Hi everyone, today I'm going to talk about Zeroth Order Non-convex optimization with Dueling-Choice Bandits. I'm Yichong from Carnegie Mellon University, and this is joint work with Aparna, Joshi, Aarti, Singh, and Artur Dubrawski. Here we focus on zeroth order optimization. The goal is to optimize an unknown black box function f with as few queries to fx as possible, without any gradient information. This is also variously known as continuous multi-arm bandits or black box optimization. One important application for this is to search for hyperparameters in neural networks. Our work is motivated by optimization with comparisons. For many optimization problems, we can obtain comparisons of the function values more easily than directly querying them. For example, in information retrieval, we can get preferences from user click data. In material synthesis, we can ask experts for their preferences on the experiments. Here we consider a case where we can query both comparisons and direct queries. So we call our problem optimization with dueling choices, since here the duels or comparisons are optional. We present our algorithm along with theoretical guarantees and the experiment results. Our target here is to optimize the function fx in the feature space X. We can have two kinds of queries. One is direct query, which is y equals fx plus epsilon. Epsilon is the Gaussian noise. We also have the comparison queries, where given two points x and x prime, the comparison oracle returns a value z, that is roughly the sign of fcx minus fcx prime. Here fc is the comparison function and can be different from the true function f. In the simpler case, if fc equals f, then it's unbiased, but we also allow it to be biased. And here we assume fc minus f is bounded in its impedance norm for some constant zeta. We assume that each direct query costs lambda L and each comparison costs lambda C. We assume lambda C is smaller than or equal to lambda L because comparisons are typically cheaper. And we have a total budget of big lambda. Our goal here is to minimize the simple regret under the given budget. The simple regret is defined as the minimum of all regret under all the iterations. If we query a direct query, it is defined as f star minus fxt if we query xt. If we compare xt and xt prime, it is defined as the minimum of the optimization gap of xt and xt prime. We put our problem in the Gaussian process optimization framework. Here we assume f belongs to a reproducing kernel Hilbert space with kernel kappa, and f is bounded in its kernel norm. We also define the maximum information gain, where for subspace A belongs to the feature space. The maximum information gain is that if we know n direct queries to the function f, the maximum possible amount of information that we can gain about the underlying function f. A seminal work in this area is COMP-GP-UCB, which just won the Test of Time reward at the last ICML conference. Here we compute the posterior mu tx and sigma tx and construct an upper bound. Phi tx equals mu tx plus beta t sigma tx. Here beta t is a multiplier. In each round, we query the argmax of phi tx. We can show with high probability that phi tx is larger than fx. If we define n lambda underbar, n lambda overbar and n lambda underbar be the upper and lower bound of the number of queries. Basically, the first one is the number of queries if we only query comparisons. N lambda underbar is the number of queries if we only make direct queries. GP-UCB can achieve a regret bound of the maximum information gain on feature space X using n lambda underbar queries, because it's label only, divided by the square root of n lambda underbar. Our goal here is to replace n lambda underbar with n lambda overbar. Since comparisons are cheaper, then we have a better sample efficiency. Our algorithm is based on UCB on the Borda function. Here we define the Borda function as the probability of the given point x beating a random point, big X. Here the big X is uniformly picked at random from the feature space. We can obtain an unbiased estimate of frx very easily by comparing x to a random point. If we assume comparisons follow a L-Lipschitz link function, that is the probability of x beating a random point x prime is a function L of fcx minus fcx prime. Then if fc equals f, we only need to optimize the Borda function fr to find the maximizer. Our comparison GP-UCB algorithm follows around this idea. We keep a posterior on both f and fr, the Borda function, mu TL sigma TL and mu TR sigma TR. We use a two-phase approach. In the first phase, we explore fr until confidence gamma. That is, we follow the GP-UCB approach, compute the confidence bound, and we do this until our confidence, beta t sigma t, is less than or equal to gamma. Here, gamma controls the exploration on comparisons. If we have gamma equal to 0, we only optimize comparisons and stay in phase 1. At the end of this phase, we compute the fr hat value, and this is a lower bound on the maximum value of fr. So after this, we have a posterior of fr as this, and fr hat. And in the second phase, we will explore f on the region where frx is larger than fr hat, so this green region here, h. And so we will only query direct queries in the green region, which is between these dashed lines. So while budget not exhausted, we will query upper confidence bound, argmax of confidence bounds on the direct query posterior, but subject to phi trx larger than 0, this green region. We can show with high probability if phi trx is smaller than 0, then it's not likely to contain the maximizer. In the case of unbiased comparisons, it is enough to optimize fr. We can set gamma to 0 and only execute the first phase. By optimizing the upper confidence bound, we can obtain the same regret rate as GP-UCB, but changing n lambda lower bar by n lambda upper bar. So we improve the sample efficiency. In the case of bias comparisons, we will have a bias of zeta on the comparisons. We also have a gamma, which is the exploration on comparisons. We can set gamma equal to O zeta in our algorithm. Then it achieves a smaller one of two regrets. Here, the first one is the regret in unbiased case plus the bias of comparisons. And in the second case, we achieve the regret of using n lambda lower bar direct queries, but we are effectively exploring this region H, where H is simply defined as a high-value region of frx. And if comparisons are of good quality, that is zeta is small, then this is our O zeta term. So so the H is also very small. So we effectively shrink the search space. We also provide an extension of COMP-GP-UCB to adapt to unknown zeta values. For experiment, we perform experiments on synthetic functions and tuning hyperparameters for support vector machines. We compare to a bunch of baselines, for example, GP-UCB, which is a label-only algorithm, kernel self-sparring, a previous comparison-only algorithm, multi-fidelity GP-UCB, where it assumes we have multiple fidelities of a function that we can query. Here we simulate the second fidelity by comparing to a random point. Our experiments shows that our methods outperform the baselines in most budget settings. And thank you. You can check out our full version online. Thank you.